under Region 10. So Region 10 is along with Bangladesh, India, China, and the whole Asia Pacific. Okay, these are the EDS members, Malaysian chapters members, okay. And then inside EDS, basically we promote lecture series and DL programs. These are the paper cutting throughout the event that we have been conducted since last year. And EDS also heavily involved in reach out activities connecting to humanity. Okay, for example, during the COVID-19, we provide some assistance to our frontliners as well. We also involve in EDS ETC education activities where you can see all the paper cutting. And we do have EDS ETC programs where engineers demonstrating science and engineer-teacher connections. Okay, for your information, EDS Malaysia has won 2018 Chapter of the Year award for 2018. And for Malaysian section, EDS was won 2017 and 2018 EDS Outstanding Last Chapter. Okay, these are the list of awards associated with EDS. And for conference, for EDS, we do have 2 conferences in Malaysia, which are ICSE and RSM. The closest one is 2021 IEEE Region Symposium of Microelectronics and Nanoelectronics, which will be conducted at the 2nd to the 4th of August 2021. We also recognize women in engineering, where in March 2021, we celebrate International Women's Day. And for those who have not joined EDS memberships, there are some promotions going on currently where you can get this promotion code ED721, okay, to get free EDS membership. You can reach us via social media such as Facebook, YouTube, Instagram, our website, and Twitter. With that, thank you very much. Back to you, Dr. Suhana. Enjoy the Let's Talks. Thank you.
Thank you, Associate Professor Dr. Ahmad Sabirin Zulfaqar, the Chair of IEEE EDS Malaysia Chapter 2021. Okay, let's move on. For today's session, we are featuring another 3 important and prominent speakers who will be talking on the area of semiconductor fabrication process. Okay, so we have Professor TS IR Dr. Abdul Manaf from UTM, Associate Professor TS Dr. Muhammad Mahidin Ramli from UNIMAP, and IR Dr. Hazian Mamat from CMOS Berhad. So it's going to be a mix of academic and industry view on this topic today. Note that there's a registration link which already shared in the chat box. Okay, please don't forget to register yourself. Okay, so we will start our session with Professor TS IR Dr. Abdul Manaf Hashim from Malaysia Japan International Institute of Technology, University Technology Malaysia. Prof. Abdul Manaf received a doctorate degree in Electronics and Information Engineering from the Hokkaido University, Japan in 2006. He has successfully developed a research laboratory equipped with advanced growth and micro nanofabrication facilities at MJIIT UTM. And in 2014, he was awarded a recognition of Top Research Scientist Malaysia, TRSM, by the Academy of Sciences Malaysia. So in his talk today, he will introduce the micro nanofabrication facilities at MJIT, including electron and ion beam based facilities. Then he will move on with his recent works and the potential research topics and method for collaboration. With that, I would like to welcome Professor TS Dr. Abdul Manaf to deliver his 20 minutes talk. Prof. Manaf, over to you. Prof.
Okay, thank you, Dr. Suhana, Chairman. Thank you also to Dr. Ahmad Sabirin, Chairman of the EDS Malaysia Chapter. Okay, I share my slide.
Okay, Prof.
Can you see my slide?
Yes, you can see.
Okay. Okay. Good afternoon. I think good evening to everyone. Okay. My name is Abdulwana from UTM. Okay. Today I would like to talk about the electron and ion beam facilities for micro nanostructure formation and device fabrication. Okay. Okay, this outline. Okay, first I would like to introduce the main micro nano fabrication facilities at the MGIE, and then I move to the our recent work on nanostructure formation using a focused ion beam, and then I would like to introduce my research interest, and also I would like to invite for the collaboration from you. Okay. Okay, this in our in UTM and GIT, we have two clean room. One is a 1K class clean room, and then the other one is a 10K class clean room. Okay, and then basically this clean room is equipped with the micro nano patterning equipment, and then we have a few equipment for the dry and wet etching, and then for metal and dielectric deposition, and then thermal annealing, and then lastly the equipment for the characterization for the material and devices. Okay, for the micro and nano patterning, okay, we have one electron beam lithography. Okay, I can say that this is the only available dedicated system in Malaysia. Okay, and then the specification of this EBL, the beam size is 2 nanometer, and then we can write a pattern down to the 10 nanometer size. Okay, and then we have two acceleration voltage. We can set to 50 kilovolt or 100 kilovolt, depending on the requirement. Okay, and then the substrate size that can be put in the system is we can have a chip size, wafer size, and also we can also fabricate our patterning the glass mask. Okay, I think this one is just to introduce what is electron beam lithography. Basically, on the substrate, we put a resist, and then we expose it with electron beam. So we write the pattern, and then we proceed with the balayment, and then you get the pattern. And then after you get the pattern, then we can move. We can proceed for the either metal deposition or etching to get the pattern, final pattern. Okay. Sorry. Sorry, ada start sikit ya. Tak jalan dia punya ni.
Prof Hana? Okay.
Yeah, sorry. Yeah. I have a problem with the slide. Okay, sorry. Oh, okay, you move now. Boleh nampak slide?
No, we can't.
No.
No. Okay, wait. I think I stopped sharing already.
Yeah.
Okay, you can see it?
Yep.
Okay, okay. Okay, the next is dry etching facilities. We have a reactive ion etcher, RIE. Okay, these gases that we have, CF4, SFC, and also oxygen. And then the maximum size of the substrate can be put in the system is 8 inches. Okay, just for information to the student, for the RIE etching, what you can get how the condition of the etching, you can get the very nice, I mean the sharp pattern, I mean the structure, compared to the wet etching. Okay. Okay, and then we have a metal deposition in facilities, which is a electron beam evaporator. Okay, and then for this system now, for the electron beam crucible, we have a 4 crucible. We can put up to 4 crucible, and then in this system also we have a resistant heating port. We have a 3 port. So meaning that you can do a continuous deposition of 7 different metal without taking out your sample. Okay, so the substrate size can be up to maximum 3 inches. Okay, so now here I think you may know the operating principle. So we have electron beam here, and then you have crucible here, and then the metal. After the melting, it will evaporate to your sample. Sample is put in top side. Okay. Also, we have equipment for the dielectric deposition. Okay, we have a plasma CVD, PE CVD. Okay, and then the gases that we have now is sealant, ammonia, and also oxygen. So meaning that you can deposit silicon nitride, silicon dioxide, alpha silicon, and also silicon oxynitride. Okay, so the maximum size of a sample up to the 3 inches. Okay, also we have RF sputtering. Okay, so now the system have a 3 target, 3 port, so we can put 3 target. Okay, and then the specification of the target is 3 inches in diameter, and the thickness is 3 millimeter. Okay, so the maximum size can be put also up to 3 inches. Okay, currently we have a silicon dioxide and also silicon nitride target. So if you have any other material to be deposited, you can bring by your own. Okay. I think you know about the principle of the sputtering. Basically, the target will be knocked out. I mean, the atom will be knocked out from the target, and then we deposit on the sample. Okay. So the material for the material and device catalyzation, of course, we have equipment for the electrical and also optical catalyzation. Beside that, also we have microscopy facilities. Okay, so for the microscopy now facility, we have a sample preparation and a microscope for the sample preparation, and also we have 2 kinds of SAM, low vacuum SAM and also field emission SAM. And then we have also a TM, transmission electron microscopy, and then we have a FIB combined with the FCM system, and then okay, and then we have also AFM. Okay, so today I would like to introduce FIB as one of the equipment to fabricate nanostructure. Okay, so FIB for nanostructure fabrication. Okay, I introduced two works. So for the first one is fabrication of quantum dot on the carbon nanotube for single electron transistor. Okay, basically the principle is okay, let's say you have a carbon nanotube, okay, and then we put on we connect to the source and drain, okay, electrode. Okay, now to get the quantum dot, basically we use a FIB to create a barrier, double barrier here. There is a mark with the cross, red cross mark here. So we create barrier here, and then you can have a quantum dot in the middle. Okay. So this is the idea here. Okay. So how we fabricate? Okay, first we make a source and drain electrode. Okay, using a palladium. Okay, here of course, as I introduced, the patterning of the electrode, we use electron beam lithography, and then for the palladium deposition, we use electron beam evaporation. Okay, and then here the gap between the source and drain is the 500 nanometer. Okay. Okay, now how to put the nanotube, carbon nanotube on the electrode. So here we use a mechanical transfer technique. Okay, this is how we do what we call it a mechanical transfer technique here. Okay, so basically we prepare the structure of silicon, PVA, and also PMMA. Okay, and then the next we disperse a carbon nanotube on the PMMA, and then we will use a tape, and then we peel off the PMA, okay, together with the carbon nanotube here. And then this tape that contain carbon nanotube, then we put on the electrode, and then we press it. Okay, and then finally we can get the carbon nanotube on the electrode. So here we can understand the nanotube is a suspended condition. Okay. Okay, this from the optical microscope we can confirm that the nanotube is only can be put on the nicely put on the electrode. Yeah, I can say that this process is very complicated. Yeah, to get well aligned of nanotube on the electrode. Okay, and then after we get a nanotube on the electrode, then we do a next fabrication is to get to make a barrier or to create a quantum dot. Okay, here so we put in the FIB system, and then we beam it. Okay, of course, here we study the dependency of the ion dots, and then also the yes, basically on the ion dots here. Okay, this is a SAM of the suspended nanotube on the electrode here. Okay, so after we fabricate this one, this structure, then we do a cauterization. Okay, and then here we study the barrier before and after irradiation of using FIB. Okay, you can see here the resistance of the nanotube increase after the irradiation, meaning that the barrier has been fabricated here. The barrier has been formed. Okay. Actually, just now I just show you the suspended carbon nanotube on the source and drain, but actually for the ACT, I didn't show you the process here. But anyhow, we just add a gate electrode during the fabrication of the source drain electrode together. So we have a source drain gate. I think. Yeah, this one, this structure. Actually, when we fabricate source and drain, we also fabricate gate electrode together. Okay, and then we transfer carbon nanotube on the source drain. Okay, so meaning that the gate actually is located at the bottom side. Okay. Okay, I move back. Okay, so by this structure, SET structure, then we measured typical Coulomb diamond characteristic. So here we can see we can observe the Coulomb diamond characteristic here, and then also we can observe also the Coulomb oscillation characteristic here. Okay, and then basically this measurement was done at a low temperature at 1.47 Kelvin. Okay. Okay, and then our idea now is after we get this ACT structure, okay, and then currently we are proceeding to the application of this ACT. We believe that this kind of device can be used as a mechanical resonator. So now it's under testing. Okay, I move to the second part. We use F5E to fabricate graphene nanohole, and then also silicon micro pore. Okay, so for the DNA biosensor. Dr. Sana, berapa lama saya ada lagi?
Can I give you another 5 minutes, Prof?
Okay, move. Okay, so for the silicon micropore, okay, of course we use F5E here. Okay, so let's say we have a sample here, substrate, silicon and silicon nitride, and then first we do a tining, and then a polishing, and then we get this structure. Okay, and then we proceed with F5E to get the conical shaped micropore. Okay, I'll show you the next one. Okay, this is actually a fabricated conical shaped micropore. Okay, actually it's a second two-step. First we get the big conical shape, and then finally we make a micro hole here. Okay, so this is a schematic here, you can see here, and then the idea is after that we put a graphene. Okay, I show you here. Okay, we put a graphene on top of the conical shape micropore, and then later on we proceed with another F5E to make a hole, nano hole here. Okay, and then with this structure, then we proceed with the DNA measurement. Okay. So this graphene that have been transferred on the micropore, okay, and then we test how the characteristic of the hole. Basically, we change the time of the irradiation, okay, and then this actually the fabricated nano hole, graphene nano hole on the silicon micropore, okay. And then when we proceed with the measurement, okay, we can have a characteristic sensitivity of the sensor. So the sensitivity is around 100 nanoampere per microliter of DNA. Okay, so now here I can say the silicon micropore and also the graphene nanohole both are fabricated using a F5E. Okay. You can see from the publication for the detail of that work. Okay, the last one part is I just want to introduce the research interest of our group. Okay, this is the list of our current research now. Okay, and then we welcome collaboration from other university also. Okay, any topic. If you have any topic in two-dimensional material and also semiconductor, of course, and then also the devices, okay, because we have a facility for the device fabrication also. Okay, and then this is my proposal. How do we can start a collaboration? Of course, we can partner for the research grant application, joint supervision of postgraduate student, and then joint publication. Okay, so I can say that I'm happy to accept any collaboration, and then I hope you can consider MJIT as a platform to execute and realize your idea, especially to young lecturer or young researcher. Okay. And then also I welcome any new enrollment of master and PhD students. So you can disseminate to your student. Okay. You can contact me if you want more detail about the facilities. Yeah, okay. I think that's all. Thank you, Dr. Sana.
Thank you, Prof. Mana, for a comprehensive overview of MGIT facilities and the research you all are conducting over there. Note that I will take all the Q&A after all the speakers finish their presentations. Okay, there's
Okay.
also a Google registration form shared for the audience to fill in. Please fill in the form and IEEE-EDS will provide you with a certificate of attendance. Okay, thank you, Prof. Hana. Okay,
Okay,
moving
thank
on.
you.
Okay, moving on, we have our second speaker, Associate Professor T.S. Dr. Muhammad Mahidin Ramli, who hails all the way from UNIMED, Perlis. Dr. Muhammad Mahidin Ramli is an Associate Professor at Faculty of Electronic Engineering Technology, University Malaysia, Perlis. He is also Head of Electronic and Green Materials, EGM Research Group at Geopolymer and Green Technology Center of Excellence. He completed his Master of Engineering Science from University College Cork, Republic of Ireland in 2008 and received his PhD from Advanced Technology Institute, University of Surrey, Guildford, United Kingdom in 2014. He was once appointed as a process engineer in Siltera, Malaysia, Sendirian Berhad and project manager for Nanorian Technology, Sendirian Berhad. Areas of his research include the synthesis and characterization of graphene and synthetic graphite that are utilized in gas sensor and biomedical devices. Over 95 technical publications are published by him. He has received more than 1.2 million of research grants over the years. Besides, numerous awards are won, including gold medals and special awards in international invention exhibitions. Without further delay, I would like to invite Associate Professor T.S. Dr. Muhammad Mahidin Ramli to talk about his research in semiconductor processes. The title given is Graphene for Semiconductor Fabrication. Is it a possibility? Okay, over to you, Associate Professor Dr. Muhammad Mahidin Ramli.
All right, thank you very much, Dr. Sana, for a very kind and very long introduction. Thank you very much. I think let me share my slide first. All right, Assalamualaikum warahmatullahi wabarakatuh, and good evening to all participants for today and my fellow speakers. So my name is Muhammad Mahidin Ramli. I'm basically affiliated in the Center of Excellence Geopolymer and Green Materials, as well as Faculty of Electronic Engineering Technology, as well as Institute of Nano Electronic Engineering, all from UNIMED. So basically, our group, the main research area of our group is basically synthesizing the graphene. So we basically focusing on two different type of graphene production, which is CVD method as well as the chemical exfoliation method. And then we also explore on the what we call it from waste to wealth. Means that we basically use biomass waste and then we turn into a graphene. For example, currently we use oil palm trunk, and then we use palm kernel shell as well as the empty fruit bunch, and then we turn those waste into a graphene. And then we use our own graphene in order to apply in our electronic applications. As been said by Dr. Sana just now, we apply on the gas sensor as well as biomedical sensor. So for this evening, basically, I just want to give you an overview, just a short overview for the next 20 minutes on how we basically try to fit in graphene into the semiconductor fabrication. Is it a possibility? The short answer, I think, is yes, but the long answer, I think it will need well, a lot of research, a lot of fundings and grant and so on, a lot of money basically in order to realize and in order to integrate graphene into the semiconductor fabrication. Okay. So before that, we know that silicon has been a dominant material for the past, I think, more than 5 decades. And then it's tough ask basically in order to replace the silicon. But nevertheless, we have one day, we get no choice where we have to replace the silicon. So one of the materials that been thoroughly researched by now and become a hot material is a graphene. So before that, just a hindsight of what do you mean by graphene. So basically, graphene is one of the atom of carbon, where we have the carbon atoms are well arranged in the hexagonal lattice. So when you stack together, then you can get graphite. So basically, we can get the graphene from the graphite. Why graphene becomes so unique? So this is basically adapted by the National Graphene Action Plan 2020, which is headed by, launched by MOSTI, anchored by Nanometer Berhad. So there are a few properties, there are a few uniqueness about the graphene. So nevertheless, if you look at into here, the one that we wanted to focus for this evening is the electronic ability and electronic properties of the graphene. There are two properties that we have to look into in order to one day to replace the silicon. The first one is the high electron mobility, and the second one is the high electrical conductivity. So other than that, maybe we can look into the thermal properties and thermal advantage of the graphene, where it will have a very excellent thermal conductivity. And with that, it will enable the graphene to use in any application, for example, the heat sink. And then the structural and the optical properties. So if you look at here, we get all the values here. If you compare the graphene and then the graphene oxide by using the chemical exfoliation, and then we further reduce the graphene oxide, and then we compare with the silicon value. For example, here we have the electron mobility. So if you look at here, this electron mobility, if you compare with the silicon, of course, it will beat the silicon and become a really good and ideal candidate in terms of the electron mobility. And then if you look at into the electrical conductivity as well, okay? And then if you look at into the shear resistance as well. So those numbers and values in theory, okay, in theory, so basically it can easily and overcome and replace the silicon in our semiconductor fabrication process. So with all those properties and uniqueness and the advantages of the graphene, what are the potential applications that we can look into? Okay, so we can have the energy applications, we can have the chemical application, the medical sectors, structural sectors, and especially in the electronic sectors. So these are basically the applications that we can look into, apply the graphene into this kind of applications, electronic application. For example, we have the transparent electrode, we have the shielding material or shielding radiation, EMI shielding, and then we have the thermal or heat sink, and then we have as a conductive inks, we have the digital electronics, we have the photo detectors and lasers, especially in photonic applications, and then we have the RF electronics in the communication engineering applications, as well as the non-volatile memory. So next, if we look into the typical IC fabrication process flow, of course, it will start with the design and then we go to the mass fabrication. And then when it comes into the IC fabrication process, of course, it will involve, first of all, it will involve a lot of high temperatures, normally between 550 to more than 1000 degrees C. So those temperatures basically will give in a high impact into the graphene. So that's why we have to look and try to overcome the first factors in integrating the graphene into the semiconductor process, which is the temperature first. So if you look at into the photolithography process, the thermal process, especially for the oxidation, growth, and so on, and then the implantation, the etching process, the dielectric, the chemical mechanical polishing, the metallization process, of course, we have a lot of things that we have to ponder, a lot of things that we have to look into and we have to think about before we can integrate the graphene into the fabrication process line. So we all know that a standard CMOS process flow basically divided into two process or two lines. The first one is the front end, the second one is the back end process. And then it can be up to 500 or 600 process steps in total in Fab Foundry in order to fabricate from silicon dioxide layer starting from the bare silicon wafer up until the pad layer or preservation layer. Can be 500, can be 600 process step. Okay, so the question is, so where we wanted to integrate the graphene into our CMOS devices, for example, or in a broader area, how we going to integrate the graphene into our fabrication or semiconductor fabrication line. So there are two possibilities to integrate the graphene. The first one on the back-end structure, and then the second one we can integrate into the front-end structure. So if you look at into the diagram here, clearly separate between the front-end and back-end structure. So for example, for the back-end, if we wanted to integrate the graphene in the back-end step or back-end structure, so relatively it will be far away from the active area, which is our NMOS or PMOS devices. Okay? But if we try to integrate into the back-end process, it will become more easier if you compare with the front-end process, even though it won't impact that much in terms of the device performance. Okay? Why? Because typically for the back-end process, the relative temperature or the process temperature that we use is only around 450 degrees C or even below than 150 degrees C. But if we try to integrate the graphene in the front-end process, so in contrast, it needs to sustain a high temperature as a dopant activation, especially for our implantation or well creation, it will need more than or more or less 100 degrees C. Okay, and then we have to look into the contamination issues as well. Okay, and then we have to look into the what we call it the mobility of our electron. Okay, so these are basically the possible issues or possible problems that we can gather before we can integrate or fully integrate our graphene into the semiconductor fabrication. The first one is large scale and quality crystal graphene production. So as I said before, in order to produce the graphene, of course, there are a lot of methods. For example, we have the what we call it the chemical exfoliation, mechanical exfoliation, Scotch tape, for example, or by using polymer, for example. And the second one, we have the CVD process, which is the most or the highest quality of the graphene that we can get. And then we can have the chemical exfoliation, and then we can have epitaxial growth, and then we can have laser ablation process, just to name a few. But the problem is, or the issues here is, when we wanted to integrate the graphene, so we have to have a method that can consistently produce a high quality crystal graphene if we wanted to replace the silicon. Okay, so the next problem is the dielectric environment. So we all know that basically when we try to attach our graphene on top of a silicon or silicon wafer or silicon dioxide, they only exist a physical attraction or physical bonding only. Means that there is no chemical bonding, means that there's only it's a non-covalent bonding, basically just a physical bonding. So means that for the next subsequent process, we can risk or we have the issues and possibility for that graphene layer to be delaminated, for example, to be folded, for example. Okay, so when that happens, of course, the performance or the properties of the graphene become different. So we have to overcome that kind of issues first. And then the next issues is the electrical contact. Okay, So this is something to do with the contact resistance. So we all know that the ideal case, we need to have the contact resistance significantly lower if you compare with the overall resistance of our devices. So that's why we have to look into the metal deposition technique on top of the graphene, and then we have to able to control the work function of the material or of the metal that we wanted to deposit on top of our graphene layer there. And then if we wanted to go for the highest quality graphene production, which is the CVD, then we have to master, or we have to find a way in order to transfer the graphene film from the CVD into our CMOS devices, for example. Okay, so this is particularly tricky because it will involve a lot of methods, and then it will involve, for example, if we wanted to produce the graphene, so we use the CVD, so it will become, we will grow the graphene on top of a different type of substrate. So in order to transfer, so there are a certain process that we have to go through in order to transfer the graphene film on top of our devices. So if we can find a good solution in order to transfer that, of course, there are a few papers that are talking about the transfer method. For example, they use the PDMS in order to transfer from the substrate, one substrate into another substrate. But the question is, when we try to integrate into the fabrication process line, is it doable or is it feasible? So that's the question. And then we all know that the band gap of the graphene is equal to 0. So we have to find a way in order to easily engineer the band gap of graphene to become a semiconductor. So basically, most of the researchers, they agree that graphene is a semi-metal because of the fact that the band gap is equal to 0. So we have to find a way, and then we have to find a doping process that we can integrate into the fabrication process line. And then these two basically are industrial issues. So in order to change, or in order to replace our graphene into the silicon, so basically we need a large amount of capitals and funding for the fab foundry. Okay, and then of course there are integrated value chain that comes with fab foundry. So we have to look into that as well. Okay, so all in all, if we wanted to make a prediction, so the near term, the graphene integration that we can think of, or that can we explore into within the next 5 to 10 years is by having interconnection. We stay with the copper as an interconnect, but we coat the copper with the graphene. So by having that process, by coating the copper with the graphene, basically we can improve the reliability of our interconnection or interconnects, and then at the same time we can speed up at least by 30% of the interconnection speed. Why? Because currently we are using the tantalum nitride metal, okay, in order to coat our copper. So this is basically the improvement, or this is basically is a prediction of the improvement or of the graphene integration that we can look into. And we have predicted that in 10 to 25 years, so maybe we can replace the silicon. Okay, so this is basically adapted from a Nature paper by Daniel research group. So this is one of the possible solution on how we integrate the graphene, not on the lab scale, but on the industrial scale. For example, they choose to integrate the graphene into the backend process or structure. So first of all, this is our structure, the CMOS structure. And then they transfer the graphene from the CVD process, from the substrate, the catalyst into the CMOS. And then after that, they do the transfer patterning, photolithography process. And then after that, encapsulate the graphene with a dielectric layer. And then after that, they have to create the via, and then they have to sputter the interconnect. Okay. So this is basically one of the example of on how possible solution in order to integrate the graphene into our semiconductor fabrication process. Okay, so if you look at here, this is basically the roadmap that been launched by a graphene flagship by the EU. If you look at into here, so they have predicted in 2030 they can have a logic devices, and then before that 2023 they can have a flexible devices, and this is the near future, which is more or less next year, which is the low cost printable electronics. Okay, so with that, thank you very much.
Thank you, Dr. Muhammad Mahidin Ramli, for the enlightening talk on the possibility of graphene to be embedded into the semiconductor CMOS fabrication line. Okay, so let's move on. We have our last speaker for today's session. IR Dr. Hazian bin Mamat, a senior engineer at NIMOS Berhad. IR Dr. Hazian received his PhD in microelectronic and nanoelectronic engineering from the University Kebangsaan Malaysia in 2018, a master degree holder from UNIMED in microelectronic engineering. He has been approved for professional engineer IR from Board of Engineers Malaysia in 2014. He is member of IEEE since 2008 and promoted to senior member of IEEE in 2015. Since 2010, he has been in the committee of IEEE-EDS and Communication Society and actively involved in international and regional conferences organized by EDS. His research interests include semiconductor process, internet communication, sensor packaging, wireless sensor network, semiconductor process, CMOS process, and semiconductor defect. Okay, so today you'll be talking about an interesting topic about defects in semiconductor process. So I would like to welcome IR Dr. Hazian bin Mamat to give his talk. Over to you, Dr. Hazian.
Okay, sorry, got mute. Okay. Sharing. Okay, thank you very much. Okay, thank you very much to our moderator, Dr. Sohana.
You're welcome.
Yes, okay. Can you see the slide?
Yeah, we can see the slide.
Okay. Okay, it's my turn now to deliver the talks on the defects in semiconductor process. Okay, okay, let's start the. Okay, this is my content. It is introduction, semiconductor defect. We are two high resistant cosmetic defect, and the last is conclusion. Okay, as an introduction, all semiconductor, whether by design or by accident, contain defects. The fundamental property of defects, such as impurities, native defects, extended defects, affect broad range of application. this technologically important defect may be introduced during the growth and processing. Okay, okay, this is the, can you see the slide move?
Now we are looking at the first slide, Doctor.
Oh, still, okay. I think I need to change the, right. How about this?
Okay, now we can see the slides moving.
I cannot do the slideshow. Okay. Okay, move to the type of semiconductor. Okay. Actually, for the semiconductor primary products, there are a few categories such as memory, microprocessor, integrated circuit, and then also SoC, silicon chip. Okay. Actually, what CMOS is doing over the years, we have produced the A6 16K at earlier years, and then we have the presence sensor, we have the photodiode, and also CMOS logic devices. Okay, and this picture here is one of our products, which is used in the agriculture, which is this one is the what we call that, this one is modboard, which is used to connect with the agriculture sensors to detect the NPK and temperature, oxygen, and everything. Okay. Okay. So before we go to the defect, we need to know the yield definition, which is the defined as the ratio of the number of product that can be sold to the number of product that can be manufactured. Okay. Estimated typical cost of modern 300 mm or 12-inch wafer with a 0.13 micron process capability is about 2 to 4 billion. For your information, CMOS through the subsidiary MySem Semiconductor, we have two fab, which is Fab 1 and Fab 2. Fab 1 is capable doing the 150 mm or 6-inch wafer, and then the Fab 2 is capable doing the 200 mm wafer or 8-inch wafer with the capability for the process up to 0.25 micron. Okay. So the cost for the Fab 1 loan, for the equipment loan, is about 100 million, and then the supporting like facilities, manpower, raw material, and everything will be easily up to 200 to 300 million. That one is for Fab 1. Okay. For the Fab 2, for the equipment only, is cost about 500 million because we have two lines of equipment. In Fab 1, we have one line, single line, which is when we have equipment down, then everything start. But for the Fab 2, we have two line of equipment, so we can have a flexibility there. And the total cost for the Fab 2 is about approximately 1 billion, together with the IWT and everything. Okay, so with a huge investment, that's why we need to have a zero defect for the production line. Okay, so that we can make profit. Okay, just to share with you, this is the fabrication step as shown by my panelists. Okay, we have a wafer fabrication, probe testing, packaging, and then the final testing. Okay. For the each station, we have inline monitoring to check for the defect. So at this station, we have the automated inspection machine to check for the particles, discoloring, surface thickness, inequality, and others. Okay. And this is the typical line and die-in, which is produced by University Berkeley. If you can see here in the CMOS logic, which is been produced by MIMOS, is very much correlated because we have this number, average score of about 90% during the line yield, and then after the die yield, we got about 70 to 80%. Okay, semiconductor defect can be detected by, as I mentioned, that one machine or automated optical inspection during the processing in line. Okay. The first type of defect that can be found in the semiconductor is associated with the material used, which is coming from the source of the material, gases that we use. Due to the fact that the device solely depends on the precise makeup of the chip, any impurity found in this device will damage its function. Okay. Any other defect might not be related to the material, but it is mechanical integrity, which is a crack on the semiconductor, which is caused by stresses that can make it malfunction. This problem likely can be detected by use of dye penetrant testing and acoustic microscopy. Okay, the third type of defect, which is can caused by the defective electronic present in the chip. Tracking this defective electronic is hard because most of component and technique choose to adopt the indirect tactic to examine the package. This is talking about the complete chip in the package. For instance, techniques such as curve tracing is used to determine the change in the chip output from the anticipated output of the functional chip. Okay. Okay. Continue device miniaturization in the semiconductor industry and trend to the larger and larger die size mean that particulate contamination has an ever-increasing impact on the yield. Okay, if we go to the trend of the size of the wafer, we have 100 mm to 150, from the 150 to 200 mm, and from 200 mm to 300, and then now the latest one is 450 mm, which is supposed to be introduced in 2018, but it's not happened because of cost and cost of to build a foundry is very high. Okay. But as we know that if we have a larger size of a wafer, we can keep the number of the malfunction chip or defect to the lowest one. That's why the foundry is getting to have a bigger and bigger size of the wafer. The other main contributor to the yield loss include the design, margin, process variation, and followed by the photography errors and material wafer defect. The dramatic decline in the contribution of people to particular problem in the fab can be attributed to better education and training, adherence to the clean room discipline, and less direct contact by people due to the use of automation. Okay, now we move to the random defect. Random defect can be traced back to the tools, the people's process, and the process chemical and the gases, or the clean room itself. Over the years, clean room technology and the purification process material has been improved so dramatically that the majority of contamination in the leading edge fab today is due to the process and tools. You may ignore the background sound noise. However, for the many existing fab, clean room contamination remains significant and yield limiting factor. Okay, this is the sources of the wafer level contamination. You can see over the years, the clean room is getting smaller and smaller. Same to the equipment, because we have more sophisticated equipment which is do the automation. And for the people also getting smaller because we can train the people to do a better job, better work. And the most important thing is the processes, which is getting bigger and bigger. Because you know that we designed the circuit to the sub nano, to the smallest that we can. That's things the source of the level of the contamination come. Okay, this is the wafer map, for example, to show to you that the defect may happen in anywhere in the wafer. And what's the defect there? It's not only on one die. It may affect the surrounding chip. Okay, and this is the cluster defect, which is you can see that there is a defect on the bottom and also on the upper level. This is example of the patterning defect, which is come from the lithography process. Not all of these defect are killer defect, but it may affect some of the function of the microchip. Okay, chip malfunction. Catastrophic yield loss, there are functional failures such as open or short circuit which cause the part not to work at all. Extra missing material particle defect are the primary cause of the such failure. The feature of the bridging fault show after this. Okay. Critical area is used to predict the type of yield loss. Okay, this is the bridging defect. See from the same scanning electron microscope, you can see that on the metal tree there is a bridging defect. Okay. Now I'm going to share with you the improvement project on the defect that we found on the 0.5 micron logic device product. The particles from the plasma etching and remaining photoresist from the lithography process is not well treated, become the disaster to the IC fabrication. The smaller gate length, the more sensitive it will be and the tougher the cleaning process. Therefore, every cleaning step must be tuned to the optimum to clear all the unwanted particles and photoresist prior to the net process. The 0.5 micron logic CMOS product is the first product qualified in CMOS Fab 2, which is on the 200 mm wafer foundry. Okay. So during the development, we're facing the low yield problem due to the via hole not fully etched and obstructed by particles and then the remaining photoresist. This caused the via2 higher resistance and bad yield. The improvement on the cleaning process, i.e. solvent and plasma, helped to increase the yield to more than 85%. Okay, during the qualification of 0.5 micron CMOS found the parametric yield are not stable, which is 50%, which is our target for the new product is more than 80%. Okay, this is the graph for our product during the early stage. You can see the first few lot is having a very high via resistance, and then after we do the optimization on the cleaning process, solvent cleaning process, then we can have a good resistance below than 10 ohm. Okay. Okay, this is a lot that we have, quite a number of lots. Okay. And this is the FSM image for the back via. You can see here, there is a leftover photoresist and other particle inside the via. And this is a good via after we do the optimization on the cleaning process. Okay. Okay, the conventional post VR2H cleaning method includes a plasma resist stripping process to remove the photoresist layer followed by solvent cleaning step. The conventional cleaning method was found to be ineffective in removing the byproduct completely, even with longer solvent cleaning step. Okay, it was thought that the byproduct compound had become hardened when it was subjected to high temperature plasma resist process directly after the VR2 process. Okay, so our new finding is a new post-VR edge cleaning method that comprised of preliminary solvent treatment prior to conventional cleaning. What method was proposed and experimented, and we found that inserting the brief solvent cleaning step before the plasma resist stripping process had significant effect in removing the byproduct in the VR hole. And the new post-VR2 edge cleaning method was able to improve the VR2 resistance to less than 6 ohm per hole, and this had helped increase the product yield to more than 85%. Okay. And then the higher also found stable during 15 consecutive engineering log. Okay. And actually, we have patented this process with the Malaysian Intellectual Patent Office. Okay. Now I'm going to share with you the imperfect processing. Imperfect processing can occur primarily due to the equipment malfunctioning and wrong sequencing of wafer. Wafer mishandling by the operators can cause wafer damage and gross error in the wafer. In modern process of yield management in semiconductor manufacturing throughput, yield loss is typically very low as most of the stages are automated and there is very less chance of human error. Okay, this is the example of the cosmetic defect. This is pitted nitride, which is caused by CVD system during the nitride deposition. And this one is the particles caused by the from resist crystallization. It should not fully remove, resist not fully remove from the process. And then this one is the metal discoloration, which is caused by total waft fully closed, which is during the process of metal deposition. Okay. And then the conclusion for today's talk is yield optimization has long been regarded as one of the most critical yet to attain the goal, thus a competitive advantage in the semiconductor operation. According to the integrated circuit engineering, yield is the single most important factor in overall wafer processing costs. As incremental increase in yield significantly reduce manufacturing costs. In this regard, yield can be viewed as a closely tied to equipment performance, process capability, operator capability, and technology design and complexity. Okay, tighten control over the contaminant and the production process are necessary to increase the yield and also to keep down the defect. Okay, contaminant may be the chemical contaminant or be dust particle. Killer defects are those caused by the dust that cause complete failure of the device, such as transistor. Okay, there are also harmless defects. And a particle need to be one of five to the size of the features to cause a killer defect. Okay, chemical contaminant or impurity including heavy metals such as iron, copper, nickel, chromium, and others. Okay, it is important for those elements to not remain in contact with the silicon, as we know that cost of operation in fab is quite high. For example, like the pen used in the clean room is a special pen which is designed for the clean room, which don't have the sodium inside. Easily can cost about 20 ringgit per pieces. And also we need to use the special notebook inside the, you cannot bring any kind of the paper or notebook to the clean room because it can cause a particle and then everything and problem to the production line. Okay, I think that's all from me. Okay, thank you very much. Okay, over to Dr. Sahana.
Okay, thank you to IR Dr. Hazian. We have learned a lot on the defects perspective in use while fabrication and methods of mitigation as well. It's such a different scenario when you need to deal with semiconductor fabrication from lots to another lots. When we researchers, we need to deal only one wafer to another wafer. So thank you again for your talk. Really appreciate it, and thank you to all of our speakers today. Now I'd like to open question and answer. There are actually several questions from the chat box. Let me just read from the first. Okay, from Ain Kamsani. In your opinion, will graphene-based device require different working principles in comparison to silicon-based device? If it is expected to replace silicon in CMOS transistor in the future? I believe this one, this question is directed to Associate Professor Dr. Muhammad Mahidin, I think.
Oh yes, thank you. Thank you, Dr. Sana, and thank you to Dr. Ain. I think I already answered that in the chat box, but never mind. I think let me see the question first. Oh, so basically the working principle is very similar to the one that we have for the silicon-based devices. Okay, but there are a few issues that we have to look into, that we have to turn, for example, the band gap, for example, the contact resistance and so on. But in general, yes, they are in a similar working principle. It is expected to replace the silicon. Well, based on the roadmap, yes, but I don't think it will replace the silicon in the future. So based on the roadmap developed by the EU and as well as MOSTI, I think it requires at least 15 to 25 years, 20 to 25 years, in order for that technology to mature. There are, of course, there are a lot of graphene-based devices. For example, our group as well, we develop single electron transistor using the graphene by the CVD process. But that only on the single device level, I mean on the lab scale, and only 1 or 2 or 3 devices. But when we try to transfer from the lab scale into the mass production, into the fab foundry, so there are a lot of issues that we have to look into, not only on the processing issues, not only on the technology issues, but as well as on the what you call it, the human capitals and the funding and so on. Hope that answer. Thank you.
Okay, thank you so much, Doctor. Sorab has also asked a question. So I believe Prof. Manaf already answered, right, Sorab? Okay.
Dr. Sana, I answered one question from him, but the last question I didn't understand. I cannot get what he's trying to say here. Can we achieve it in an operational principle rather than content dot? I cannot understand the meaning of this question.
Sorab, you mean by this question?
Yes. First of all, Assalamu alaikum to all. Dear Prof. Abdul Manaf, my question is, if we want this device to operate in a room temperature, I mean not in a low temperature, in this case, the quantum dot principle will apply or not? If it is not applied, then do we can have a resonating at this room temperature?
Okay, actually for this ACT to work as a mechanical resonator, Okay, so the content size should be less than 10 nanometers, something like that. Okay, so but currently we are testing at low temperature because the dot size still larger than 10 nanometer. Okay, okay, and then your last question, what is it?
It's about if we want to apply the same device at room temperature. In this case, the quantum dot will be applicable or not? The principle of the quantum dot.
No, it cannot function as a ACT at the room temperature right now here.
Yeah. Okay. 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 So another question, please, Prof. What is the way you are using to detect the output from the device?
The output of the device, what do you mean?
How do you measure it? Is it?
Yes, exactly.
For the resonator or?
Yes.
Okay. I share you the slide.
Yeah.
Okay. Okay.
Yeah.
Can you see this? Okay,
Yes.
this is a measurement setup that we are using now for the resonator. Okay, you can see here we still insert the device in the low temperature chamber, yeah. And then we connect to the we have a low pass filter and then also voltage source here. And then we measure, using this we have a current. There is a schematic, the roughly schematic of the measurement setup now. Yeah.
Okay. Thank you, Prof. Thank you, Prof.
Okay, thank you, Prof. Manaf, for the answer. We have another question from Dr. Nafariza to Dr. Hazian. I understand that Malaysia is moving forward to support the back-end process since it's more valuable. If we compare with front-end that is too expensive, how do you foresee the situation, Dr. Hazian?
Okay, thank you very much to Dr. Nafariza. Yes, as we know that the front end is too expensive for us to bear the cost. So, yeah, as we know that now the government is looking to fund on the back-end process, which is the packaging and also the wireless sensor, the things such as wireless sensor that were more to the IoT and more than not on the front end, which is producing the chip. But there is still a budget for that, but not as per previous year. So I think that's a good move from our government to move forward together with the market. I mean that we can save our budget from the front end and then invest into the back end processes. Thank you. Is that answer your question?
Okay, Dr. Nafariza, does it answer your question?
Thank you.
Okay, we still have time. We still can have questions if you have. To all our speakers. So while you think about questions, I would like to pull your interest to the, if you can see here, we have a poster of IEEE grant opportunities. Okay, so there are various grant opportunities from IEEE. And if you want to know more about how to apply these grants, we are conducting a workshop this coming Thursday. Okay, if you are free, please join this workshop. So any more questions? Okay, so now it's already 4:30. On behalf of IEEE EDS, I would like to thank all of you for your time to join our session. Thank you also to all our speakers for your time as well. It's a great honor to have all of you here in this platform. Is it possible if we all take a photo before we leave this platform? Can you all open the camera? Shall we take a group photo?
Okay, Dr. Su, I will take the photo, yeah?
Okay.
Dr. Nafas, sihat ha?
Baik, alhamdulillah.
Sini PKPD.
Wah, itu kat tepi pantai tu cantik tu.
Hari ni 3,000 cases Selangor.
Tak boleh buat apa lah Selangor ni.
Always a champion.
Selangor boleh doa lah.
Kita boleh buat, kita keluarkan.
Berdoa dan berusaha.
Ya.
Ada orang nak keluarkan Selangor daripada Malaysia dah ni.
Ada. Dia kan nak Maghrib pergi Perlis lah.
Kita buat rombongan pergi Perlis je lah.
Boleh. Kita memang menerima.
Boleh.
Dengan hati terbuka, tangan terbuka, insyaAllah.
Aduh dah.
Boleh kita pergi hostel Unimap.
Ada offer.
Ada
Pakaran ada kat dalam ni.
Minta Prof Huda sediakan kita punya accommodation.
Oh, dia apa ada kat Syalam?
Oh, ya.
Dia pun dah start situ
Dah
dah.
ambil gambar kan?
I dah ambil dah. I dah ambil gambar.
Thank you,
Oh,
Dr.
okay.
Thank you. Okay.
Thank you banyak, thank you Prof Hana.
Okay, thank you.
Thank you
semua.
Thank you, Dr. Maidin.
Terima kasih komiti, terima kasih
Please
semua.
stay safe and vigilant with your loved ones. Take care. Assalamualaikum and have a nice day.
Thank you Dr. Suhana.
Terima kasih. Thank you,
Thank
Dr.
you
Suhana.
Dr. Zabirin.
Thank you semua.